Welcome. This is the 2022 Morningside Institute Geometry course. The title of the course is Advanced Topics in Plane Geometry. So my plan is to introduce some useful and interesting topics, special topics, advanced topics in Euclidean geometry, in triangle geometry, in order to prepare you for the ME or USMO math competitions, the geometry part. So before we do that, let me first make an announcement. So I have a geometry discovery project which is still under construction, but we have written 2/3 of the articles. So these are the articles in triangular geometry, and you can click the link here to go to our web page. And you can click, for each topic, you can click the details, and there will be a PDF file will pop up introducing you the special topics in triangular geometry. Okay, so this course will have 5 lessons. And in the first lesson, so by the way, this lesson we will have lecture for 1 hour, and on Saturday, we will have office hours in order to prepare you for the homework problem. So each week I will post about 10 homework problems, and you can do them during the week. And if you need help, you can get the help during the office hour on Saturday, 4 to 5 p.m. Okay, so this is lesson 1, and the topics I'm going to introduce today are the following: the Manila Theorem, the Siva Lines. These are the basic series. They are not even, I think that's not even above the AMC level. It's at the AMC level. If you take AMC exams, you probably should have learned these 2 important theorems in Euclidean geometry. And its generalization, Roch theorem, and some applications including harmonic conjugate points, which is the harmonic conjugate points, and the cross ratios are important tools in geometry. So I'm going to introduce all of them and basically put them together and show you how these topics, if used correctly, will be very effective solving difficult geometry problems. So let's begin with a very quick review of the Siva and the Manila theorem. Manila's theorem was discovered much earlier, about more than 2,000 years ago, by Menelaus, who is the king of the city of Alexandria in Egypt. So this is a very powerful and useful tool in proving collinearity of points in the Euclidean plane. So let's go over with this first. So the setup of Menelaus theorem is actually quite simple. So we have a triangle ABC, and suppose DEF is a line passing through the 3 sides of triangle ABC this line intersect AC at the point E, intersect the side AB at point F, and intersect at the extended line of the side BC at point D. Okay, so with this very simple setting, we are able to get the following interesting identity. So namely, AF over FB, BD over DC times CE over EA. So these 3 ratios, if you multiply them together, you would get it equal to 1. So why this is very interesting and important? Well, you see, basically these 3 ratios, they are far apart. Okay, if you know this guy, you know this guy. So with this equation, you know any of the 2 ratios, you can compute the 3rd one. And this is a very typical question that we need to know about the ratio of the intersection of 2 lines in geometry. If you know some of them, you want to get the other ones. So I will show you some examples later on. Well, this is interesting, but this is just the part of the Menelaus theorem. The other half of the theorem is the converse theorem. Okay. So you can actually use this criterion to determine whether 3 points are collinear or not. So the converse theorem can be read as follows. So if you have D, E, F be the points on the corresponding sides B, C, C, A, and A, B, and then if this equation is valid, then we can conclude that the point D, point E, and the point F are collinear. So that means these 3 points are on one line. And we know that this is very important because there are very little tools that people can use to prove the collinearity. Okay, so this theorem gives us a very important theorem, a criterion to do so. Okay, you can click this Wikipedia to see the more details of it. Here is the question: how to prove such an important theory? Well, the proof actually is there's a general idea how to prove these kinds of, you can call it theory, you can call it a problem, how to do it. Note that the 3 ratios, AF, BD, DC, AF over FB, BD over DC, and CE over EA, they are basically far apart. Okay, it's very difficult to make them to interact to each other so that their multiplication could be equal to 1. So that's the difficult point. So the idea is that's actually the idea in the whole Euclidean geometry, is that we want to do anything to move all the interesting part together. Okay, so what I will do is basically using similar triangles, using parallel lines, to move all the ratios, to convert all the ratios into the ratios on a fixed line, on a given line. So if all the ratios on one line, they may interact to each other, you may be able to prove that their multiplication would be equal to 1. So that's the idea. Okay, so let's look at this picture. Okay, so we can draw one parallel line starting from B. Let's draw a parallel line which we call the BK, which is parallel to AC. So remember, BK is parallel to CA. Okay, and the K is a point on the line DC. So let's first assume that DEF are collinear. Okay, they are on a straight line. So this is a line, and we draw a parallel line BK so that the line hit the line DEF at the point K. Okay, so this simple additional line will help us to convert all the ratios into the line DEF. And let's see how this would work. So first, AF over FB, I claim this would be equal to EF over KF. So that's the first equation. So I'm not going to repeat why this is true. I'm not going to talk about why this is true because this is obvious that we have two similar triangles. So this triangle is going to be similar to that. Why? Because these two angles are the same, and these two are alternative angles since these two lines, BK and CA, are parallel. So these two lines are equal as well. These two lines are equal. These two lines are equal. So everything. So for these two triangles, two corresponding angles are equal, and therefore these two triangles are similar. So this is actually the basic configuration of similar triangles. Anyway, by the properties of similar triangles, we have this first equation. Okay, so now let's do the next one. How about BD over DC? Okay, so BD over DC. Well, you see another pair of similar triangles. This triangle is similar to that one. So by the property of similar triangles, we would have BD over DC is DK, let me erase that, is equal to DK over DE. Perfect. So we basically convert two of the three ratios, this ratio, onto, well, we didn't solve them, but we just convert them to the ratios on that single line. How about the third one? This is a little bit more difficult. How about CE over EA? So CE over EA. So at the first glance, you wouldn't see that they are somehow related to a pair of similar triangles, but you can do this trick. Okay, so CE over EA, we can divide it by BK and multiply by BK. Okay, so this is the trick. And once you do that, you would see that, well, CE over BK, well, you have the pair of similar triangles, that would be equal to DE over DK. Okay, so that the first part is converted to the ratio underlying DEF. How about the BK over EA? Well, again, BK over EA would be KF over EF, KF over EF. Okay, so now what we need to do is basically multiply all these together. So what we want to prove is this guy, and this guy, these three ratios, multiple them, they will get equal to 1. So let's see if this is indeed the case. Okay, so we have this guy, we have this guy, we have these two. And you see, can we just cancel them? Yes, you see DE downstairs, right? KF upstairs, KF upstairs. FE downstairs, FE downstairs. And DK and DK. So multiple all of them together, we get that equal to 1. And that proves the Menelaus theorem. And I will skip the proof of the converse theorem. Converse theorem basically says, well, if they are not collinear, you can draw a line that hit another point, presumably we call it D prime. And the D prime satisfy this condition, and D satisfy the condition by assumption, so D and D prime must be the same point, and that gives the proof. Okay, I will skip that. So that's called the Menelaus theorem. And so the next theorem I'm going to introduce is called the Siva theorem. And the Siva theorem and Menelaus theorem are dual to each other. So this terminology called duality is a terminology in projective geometry, which I'm not going to introduce, don't have time to introduce today. But at least you can see that the statement of these two theorems are dual to each other. Okay, so it's interesting that even though these two theorems are dual to each other, and we will know if you have learned linear algebra, you would realize that these two theorems are actually equivalent. But Siva theorem was discovered much later. It was discovered in 18th century, almost more than 2,000 years later it was discovered. Okay, the statement of the theorem goes as follows. Again, we fix a triangle ABC. And we assume that ADBECF we call it concurrent. So that means these three lines meet at one point. We know that in general, three lines, well, they don't meet at one point in general. But if these three lines meet at one point, then we have another multiplication of three ratios that is equal to 1. Namely, BD over DC, CE over EA, and AF over FB, that is going to be equal to 1. And now why these two theorems looks dual to each other? Because for the Menelaus theorem, we are talking about the collinearity of 3 points. And in Siva theorem, we talk about the concurrent of 3 lines. So here you replace point by lines, collinearity of 3 points by concurrency of 3 lines. So in that sense, these two theorems are equivalent, are dual to each other. Okay, so how to prove this Siva theorem? Well, what's the idea? How to do that? Well, again, these 3 ratios are quite far apart. They are quite far apart. So how to move them together? How to move the ratio into basically all the ratios into the ratios in one line? Well, if you try this a little bit, you would realize that if you draw a line starting from the point point A, and you draw a parallel line, and you extend BE and CF. Then you have this, you meet them, BE is at P, and the CF would be hit at the point Q. And then you are able to basically convert all the ratios to the ratios on the line PAQ. Okay, so how to do that? Well, with the experience we had for the Menelaus theorem, we are able to do this quite fast. So first, AF, let me write, AF over FB would be equal to QA over AFFB would be QA over BD. Okay. And so again, the last one, CE over EA would be equal to, I'm sorry here, this is not BD, this is BC. Okay, so sometimes I made a mistake. Okay, and the reason is, you see, this triangle is similar to that triangle. So this is what you would get. Okay, so let me erase the lines. And similarly, CE over EA would be equal to BC over PA. Okay, so that's basically straightforward. Not exactly move everything into one line because it contains BC. The good news is that if we multiply these two, the BC and divided by BC, one BC upstairs, one BC downstairs, they would be canceled out. All right, so you're left with QA and the PA. So the last one would be how to do BD over DC. BD over DC. Now we have experience. So what we will do is, okay, so we will see that, so BD over AP would be equal to DO divided by OA, right? So because these two triangles are similar, but then DO over OA can be converted to this guy to that guy will be equal to DC over QA. That's nice. So we use this as a middleman, then we can have a relation between BD over AP and DC over QA. So from here, we will get BD over DC is equal to PA over QA. And then we are done. So you have QA, PA, QA, BC. So if you multiply all of them together, it is equal to 1. Okay. So these two proofs are just one of the many proofs of Siva and the Menelaus theorem. In the exercises, you will have the opportunity to prove the Siva and the Menelaus theorem using area methods. We know that area methods is always the very useful method. I will also let you to prove that actually you can use Menelaus theorem twice to prove Siva theorem. So, well, I'm talking about the proofs, but you can view them as homework problems, as exercise problems that you can warm up to use these theorems. Okay, so let me give you one example as the application of Siva and we use Siva theorem as an application of Siva theorem. I discovered that myself, and I'm quite happy with that. So comparing this picture with the above picture, well, this one is copied from the above, but then we draw another two lines. Okay, we draw this DF and the DE. Okay, so they hit the line PQ at the point L and K respectively. So it was surprising to me that actually AK is equal to AL. So that part is I'm quite happy that I found that. That's quite interesting. But the proof is not at all difficult once you converted everything to to this line. So you can actually compute both AL and AK using the other ratios. Okay, so you can read this after the class carefully, but what I can tell you is AL over BD is equal to AF over FB. Good. AF over FB is one of the three ratios in the Siva theory. Okay, so AL is equal to that. Similarly, we can compute the AK, which we know that it is AKEC times DC. Okay, so the proof becomes easy. You want to prove AL is equal to AK, right? So then you divided AL by AK. So basically, it's the division of AF over FB, then BD divided by DC, and then you make this upside down EC over AE. And what's the conclusion of the multiplication of these three is equal to 1. So that you concluded that AL over AK is equal to 1. That is, AL is equal to AK. Okay, so that's an interesting exercise. But there's a special case. Which is more, I would say, difficult to prove, because you have to create those parallel lines by your own. So I learned this problem when I was a high school student. It's very interesting. So suppose you have a triangle ABC, and suppose you have CD is orthogonal to AB, CD is perpendicular to AB. We assume that. Okay, so then there's a surprising conclusion that these two angles are the same. Okay, so you can try it. Without using our method, it would be difficult to prove this theorem. Why? Because you wanted to prove two angles are the same. And it's very difficult to find how to prove two angles are the same. Well, it's very difficult because you need to, there's no congruent triangles that you can play with. There's no isosceles triangle. So you can, if you have an isosceles triangle, well, you can use the isosceles triangle theory and say, okay, so suppose AB is equal to AC, then this is the height, this is the median, and this is the angle bisector of angle A. Well, you don't have those. So what you need to do is you need to complete the picture by an isosceles triangle. So this is what I'm doing. So I just draw a parallel line and make DE and the DF intersect at KL. That's what I want to do. And apparently, since this KL is parallel to AB, then CD is the height. Okay, so you want to prove that these two are angle bisectors. The angle bisectors coincide with the height. So you basically need to prove that triangle DKL is an isosceles triangle. And how to prove that this is an isosceles triangle? Well, this is just a very special case of this, that AL is equal to AK. So you have CK is equal to CL. You can prove that. So if CK is equal to CL, then CD is a median. It is a median as well as a height. So then if the median coincides with the height, then the triangle is an isosceles triangle. So CD is also the angle bisector. And we complete the proof. Okay, so that's the interesting problem using Siva theorem. Later we will see that we can prove this by the harmonic conjugate point theorem, but this is more specialized. Okay, so one of the applications of Siva theorem is that it can be used to prove that a lot of concurrency of lines, which called Siva lines. Okay, you probably have heard that there are 5 centers, 5 special points of triangle. Okay, so among them, the most important being the centronoid. So what is the centronoid? The centronoid is the point of the 3 intersection of the 3 median. Okay, in other words, we need to prove that the 3 median means if D is the midpoint, then AD is called the median. Okay, a triangle has three medians, and no matter what the shape of the triangle is, the three medians must meet at one point. That point is called the centronoid. How to prove that? Well, using Siva theorem, the proof becomes just very simple. Okay, so because BD over DC times CE over EA times AF over FB, that's equal to 1. Why? Well, this is equal to 1, this is equal to 1, this is equal to 1. The multiplication of 1 by 1 by 1 is equal to 1. That complete the proof. So Siva theorem can be used to prove that. So there's another center called the incenter, which is the center of inscribed circle. Okay, so this is called this is called an incenter. Okay, we cannot use we can, but it's more it's different, but we can. But anyway, so we can prove that these three angle bisectors have to be concurrent at one point, and that point is the center of the circle that is inscribed in the triangle. So that's called the incenter. So generalizing the incenter, we have three excenters of a triangle. So JA, JB, JC, they are the excenters. So center them, there's a circle that is tangent to the three sides of the triangle. But its name is called excenters because it's tangent to one side of the triangle and it's tangent to other extended sides of the triangle. So there are three of them. These are called excenters. Okay, for a triangle, there is a circumcenter, okay, which is the point O that its distance to the three vertices are equal. Okay, so that's the circumcenter. And there's an orthocenter. That's another special center of a triangle. So it turns out not only three medians, three angle bisectors are concurrent, but three heights of a triangle must meet at one point. And that point is called the orthocenter of the triangle. Okay, for this one, you can try to use Siva theorem to prove the concurrency. Basically, you would compute the BD over DC, CE over EA, and the AF times FB. You want to prove that the multiplication of all these three, it would be equal to 1. You can use trigonometry a little bit because you can prove that, for example, BD is AB cosine B. Okay, so if you convert all these in terms of three sides and three angles, you will quickly see that their multiplication would be equal to 1. All right, so that concludes the first part of the introduction of today's topic. Basically, we're talking about Siva theorem, Menelaus theorem, and there are many applications. We will talk about more applications later in this lecture. The second topic I'm going to introduce you is called the rock theorem. Well, this rock theorem is by itself interesting, but I put it here because one of the application of it was in Math Olympic. The problem was in Math Olympic competition. That's one problem. But let's first state the general, make it a general statement. Okay, so let's fix a triangle ABC and let's make ADBC, ADBECF. So by the way, these lines from one vertex of triangle that goes to the other side of the triangle, like AD, this is called a CVN. Okay, CVN or Siva line. So this is obviously named after the Siva theorem. Okay, so the Siva theorem basically says that the three CVNs are concurrent if the multiplication of the three ratios is equal to 1. So let's ask ourselves a general question. So what if these three ratios, BD over DC, CE over EA, and AF over FB, their multiplication is not equal to 1. And if they are not equal to 1, obviously they are not concurrent. And then when they are not concurrent, they would have they will intersect at 3 points. And these 3 points will form a triangle. So in the picture here, that these 3 intersecting points form the yellow triangle. The Rock theorem says that the area of this triangle can be computed. And it doesn't depend on the shape of the triangle ABC, which is surprising, but it depends on the ratio X, the ratio Y, and the ratio Z, through this very complicated formula. Okay, and you will see that you can view this as a generalization of the Siva theorem, because if you see XYZ is equal to 1, so then the area is equal to 0. So that means in that case, these 3 intersecting points, PQR, are just degenerated to 1 point. So that means these 3 Sivians are concurrent. In general, the area depends on, well, this complicated formula. In particular, the far away XYZ is from 1, the bigger the triangle area. Okay, so because of the time, I have already written all the details here. You can go over with it, and basically, well, this is the place that you may want to compute. Well, the area of this guy is easy because you know the ratio, so you know this area, how large or how small the area of it is. But here's the question. I want to compute, let me just use different color. Okay. I want to compute the area of this triangle. How to do that? Well, the point is, in order to find this area, you just need to know the ratio AR over AD, right? And this is exactly the place that you should use Menelaus theorem. Okay, so AR over AD, you just need to find a triangle, AR over AD, and you can use, I think you can use one of the triangles. Let me erase that. Right. AR over AD. It basically is DA over RA. So you want a triangle here, and you want a line that going to outside. Well, if you want to know AR over AD, you just need to know AR over RD. That will be a lot easier. And AR over AD, then you will see that in this triangle and this line passing through this triangle, so AR over RD can be computed by this ratio and this ratio. And so that's Menelaus theorem. But these two ratios are known, so you are able to compute that, and you can compute AR over AD. So then you are done. So you can see the details later. But I'm going to ask you, in the homework problem set, I will ask you to prove this identity. It looks easy, but try it. If you just do it just by brute force, it will be super complicated. So the question is, for any real numbers x, y, z, we have this identity. Okay, it will be super complicated to do it directly, but there's a trick to do it. You can just do it by straightforward computation. But I would like you to use that as an exercise. A special case was called the 1/7 area triangle problem. This is in one of the Math Olympic in the past. I don't remember which year it was, but in the past this was one of the Math Olympic math competition problem. Okay, so suppose x, y, z are all equal to 1/2. So that means this guy is half of DC, CE is half of EA, and AF is half of FB. What is the area in the middle? The answer is the area in the middle is 1/7. it is 1/7 of the total area of the triangle. So using the Rock theorem, you can plug in XYZ to be 1/2 to do the computation. You can also use Menelaus theorem to compute them directly. Okay, so that basically concludes the first portion of the theorem. The second topic I want to bring to you, which is related to the ME exam, is called the projective harmonic conjugate points. So by definition, this is related to 4 points on a line and their relative positions. Okay, so first we give the definition. So suppose I have 4 points, A, B, C, D. These are the 4 consecutive points in that order, A, B, C, D, from the left to right, on a line. Then we can define something called the cross ratio. And the cross ratio is using this bracket A, comma C, semicolon, BD. Okay, so that represents a real number. That real number is equal to BC over AB times AD over DC. Okay, so at a first glance, you may see why we define, well, we could define such a strange quantity, but why should we do so? Okay, so hold it. Let's make another definition. So if this number happens to be equal to 1, then we call these 4 points are called projective harmonic conjugate points. Conjugate in the sense that the pair of points BD is conjugate to AC and vice versa. Okay, again, you have the question why. Well, there's a simple algebraic exercises that you can make use of to prove that if the cross ratio is equal to 1, then this identity is true. So in other words, AC is called harmonic mean of AB and AD. So we know if we have 2 numbers AB, so this is called arithmetic average, arithmetic mean. Square root AB is called the geometry mean. 2 over 1 over A to 1 over B. This is called the harmonic mean, right? Harmonic mean is less than the geometry mean, less than algebraic mean, arithmetic mean, okay? But then you will see that if ABCD forms the harmonic conjugate points, then the length AC is the harmonic mean of AB and the AD. Okay, I'll leave this as an exercise. So the next thing I want to explain, which means that this cross ratio, the concept of cross ratio is very important, and it will give us unexpected result in doing math competition, is the following we call the invariance, okay, of the cross ratio. Okay, so here's the picture. So if we have 4 points A, B, C, D, and suppose P is a point outside the line L1, so then we can draw PA, PB, PC, PD, 4 lines. And suppose now I have another line called L2 that intersect with these 4 lines, four line segments at EFGH. And so the theorem is that the cross ratio ACBD is equal to the cross ratio of EGFH. So that means, well, this is very interesting because no matter what the position of L2 is, the cross ratio would be the same. So everything will change, right? EF is apparently won't be equal to AB, EG is not equal to AC. Well, they are all different. But surprisingly, the cross ratio is equal to 1. How to prove it? So this is the second topic I'm going to talk about today. And in order to prove it, I want to introduce another very, very important theorem called the Generalized Angle Bisector theorem. So please remember that theorem because this is equally important and will give you surprising result in solving difficult problems. So this is called the Generalized Angle Bisector theorem. I use a little bit trigonometry to do so. Okay, So the configuration is again very simple. So we have triangle ABC, and we have one line called AD, that which is apparently a CVN, right? And so the question is, what is the ratio of BD over DC? Well, BD over DC, there's a formula. BD over DC is AB over AC times sine angle BAD, so this is the angle, and the other angle, DAC. Okay, so this is the ratio that, well, at the first glance, you may think this is why this is interesting. Well, this is interesting because we can convert the ratio to the sine of angles, and well, the ratio of AB and AC usually is supposed to be fixed because we fix a triangle. Okay, so therefore this gives the relation between the line sides, the length of the sides BD and DC, and the trigonometry. And so because of that, we can play with it. You can actually use this generalized angle bisector theorem to prove that the three heights are the same. Three heights are concurrent. Okay, so yes. All right, so why this theorem is called the generalized angle bisector theorem? Because there's an angle bisector theorem. So that is a special case. If these two are the same, if these two angles are the same, so therefore AD is the angle bisector of A, so then BD over DC is actually equal to AB times AC. So that's called the angle bisector theorem. Using angle bisector theorem plus Siva theorem, you can quickly prove that the three angle bisectors are concurrent. Okay. All right, so here we use area method to prove it. We don't have to, but we can use law of sines to prove it, but here we use area method. Okay, so first, BD over DC is equal to the ratio of the triangle area. So this is the area, and this is the area. So basically, BD over DC is the ratio of the pink area divided by the yellow area. Okay, but then for the pink area, so the pink triangle and the yellow triangle, we can compute its area using another way. Okay, so here is the formula. So if we have a triangle, so suppose this is side is B, this is C, this angle is A. So the area formula is equal to half of BC sine A. So that's another formula for the area of triangles. And so because of that, so triangle BAD is basically half of AB times AD times sine, and the DAC is AD times AC times sine here. Okay, so this is the quickest way to prove this general angle bisector theorem. If you take a ratio of these two, well, you take a ratio of the right-hand side, and the 1/2 is canceled, the AD is canceled, you are left with what we wanted. So that's how we can prove this general angle bisector theorem. Okay, so this angle bisector theorem is one of the fundamental theorems. To my point of view, it gives us a lot of applications which are useful. Okay, so it's not purely Euclidean geometric because it's related to trigonometry. But in any math competitions, we are allowed to use all the tools to solve a geometry problem. Okay, in particular, trigonometry is super useful. All right, so now let's use this generalized angle bisector series to prove that ABCD, so the cross ratio, is independent of the choice of the lines L1 or L2. No matter you use L1 and L2, well, their cross ratios will be the same. How to do that? Well, let's go back to the definition. So ACBD is BCAB ADBC. So let's remember that. Okay, BCAB. Okay, so cross ratio ABCD is equal to BC, is it BC? I forgot, AB times AD over DC. Okay, so the first one is BC over AB. Okay, what I can do is I can use this generalized angle bisector theorem. I can conclude that this would be equal to AC, sorry, not AC. We just look at this triangle. Okay, so BC over AB. So suppose this is alpha, this is beta, this is gamma. So by the angle, generalized angle bisector theorem, BC over AB would be equal to PC over PA times sine beta over sine alpha, right? Okay, so this is the first step. The second step, what about AD over DC? AD over DC. Well, this time, we can use the same angle bisector, generalized angle bisector theory, provided that this D is not on the line segment AC, but on its extended line, which is fine. We can use it regardless. Okay, first the ratio would be PA over PC still, but then the angle would be, well, the first angle would be the angle APD, which is sine alpha plus beta plus gamma, divided by, when it swing back to C, you have sine gamma. And what you see, the interesting part is that these two can be canceled out. So you are left with the ratios of, the multiplication of ratios of angles. Well, this is a complicated expression for angles, but you are sure that it's independent. Those angles are independent of the choice of L1 or L2. Whether you choose L1 or L2, the angles are unchanged. So therefore, the multiplication of their ratios would be unchanged. So that's the proof of the invariance of those cross ratios. So this is an interesting thing. All right. Okay, so this is the generalized angle bisector theorem. So because of this, we also call this PAPB, PCPD called the harmonic conjugate pencil, okay? That's dual to the harmonic conjugate points, okay? All right. And the Theorem 7 is a special case, which basically said that assume that BCD are projective, BDCE are projective harmonic conjugate points. And assume that there's a point A which is outside the line. And so that AD, AE are basically perpendicular to each other. So then we concluded that AD is the angle bisector of BAC, and this AE is the bisector of the external angles. These two angles would be the same. Okay? And so basically we use the previous formula we have. Did I erase that here? So basically the cross ratio can be converted to the ratio of angles alpha, beta, gamma. So what I will do is, let's say this is alpha, this is beta. And the fact that this is perpendicular, so that means this is 90 degrees minus beta. Okay, so put everything together. So this is what the cross ratio can be written as that, right? And so this would gives us tangent beta times cotangent alpha. So if this cross ratio is equal to 1, that forces tangent alpha equal to tangent beta. And we know that alpha is equal to beta. And so therefore AD is the angle bisector. And also you can prove that AE is the bisector of the external angle. So not this picture, I'm sorry. It should be like this. These two angles are the same. Okay. I want you to use this theorem to prove give another proof of this one I mentioned here. Okay, so basically you want to construct the harmonic conjugate point so you can conclude that this will be the angle bisector, basically. Okay. Okay. All right. So that's the last one. I want to introduce one applications. That application would be useful in math competition. So you will see surprisingly that harmonic conjugate points are there are quite a lot. So here is one of the example. So assume that LMKN is a quadrilateral. So I draw a convex quadrilateral, but it really doesn't matter. And so any quadrilateral is made by 4 sides. And these 4 sides, actually, the 2 opposite sides will intersect at another 2 points, A, B. And so basically you have a picture we call the complete quadrilateral, which is made from 4 sides, 4 lines. They intersect at 6 points. So that configuration is called the complete quadrilateral. For complete quadrilateral, you have 3 diagonals. Okay, this is opposite to a quadrilateral, which you only have 2 diagonals. For complete quadrilateral, you have 3 diagonals. So apparently LK is a diagonal, MN is another diagonal, but there's one more. The line AB is the 3rd diagonal. So what is the usefulness of this configuration? Well, the cross ratio of ADBC is equal to 1. So that means these 2 diagonals cut the 3rd diagonal. They meet at the 3rd diagonal to provide the harmonic conjugate of AB, give the harmonic conjugate division of the 3rd diagonal AB. Okay, how to prove that? Well, basically we will use Manila Theorem and the Siva Theorem all together. Okay, so we consider triangle LAB. In this triangle LAB. So since M and C are collinear, by Manila Theorem, we will have LM, MA, ACCB, and the BNNL is equal to 1. Okay, and so this is the first step. We use the Manila Theorem, but we can use Siva Theorem as well because LD, LD, LN, BM are basically concurrent at a point K. So we have LMMA, ADDB, BNNL, that's equal to 1. And comparing the above 2 equations, we would have, okay, you can see that these 2 are in common. These 2 are in common. So we would get AC over CB times AD over DB is equal to 1. And so therefore the cross ratio is equal to 1. So that completes the proof. So this theorem is interesting because you basically draw an arbitrary quadrilateral, then just using those line intersections, you will easily construct the harmonic conjugate points. So harmonic conjugate points exist almost everywhere. All right, so this is the last example is what I am going to talk about. So this was the theorem I mentioned. This was the exercise I mentioned before. But then you are able to prove that this angle is equal to that angle if you are able to prove that this H and G harmonic conjugate divides EF. Or in other words, if you can prove that EHFG are harmonic conjugate points, then because these two lines are vertical, by theorem 7, we know that these two angles are the same. But how to prove that these two are harmonic conjugate points? Well, very easy. You can just interpret it as, well, this is a diagonal, and this is a diagonal, this is another diagonal. So these two diagonals intersect with the third diagonal and give 2 points, which gives you harmonic conjugate point. That's the theorem we just proved. Using that, we are able to prove EHFG is a harmonic conjugate points, and therefore these two angles are the same. Okay, so I guess today I introduced the three concepts. Okay, Siva and the Menelaus theorem, that's the basic you need to know. Rock theorem is the extended theorem of Siva and the Menelaus, and so the cross ratio is actually important because of its invariance. You can basically jump one cross. If you are able to compute one cross ratio, you can do the other. So in the exercises, you will have more opportunity to play with that. Okay, so that's all for today's class. Thank you for listening.